Martin-Heirer and Massimiliano-Gubinelli. So now we have actually two theories. So one by Martin, which is called regularity structures, and one by Massimiliano, which is called paracontrolled distributions. And both give the following. So we have a proper notion of solutions, which I said before was even a preliminary problem to the possibility of giving results of existence and uniqueness. So then we also have existence and uniqueness of such solutions for a class of equations. And so this is maybe one of the interesting points. So it is a non-perturbative approach. And the outcome is a map which, to a realization of the noise, assigns a solution psi, which depends on psi. So in this sense, this is a random variable with values in distributions. Okay. Okay, so maybe I will come back to this later, but it is very important to stress that in this theory, we build an object which is not, say, a formal solution or a formal power series. It is really a random variable with values in distributions, which satisfies, in some sense, the equation, etc. So probably I still have, yes, some slides on this. Now, renormalization appears in this context because the construction of solution works in this way. First, you regularize the noise by some form of modification. Maybe this is covering. Okay. So psi epsilon is a rho epsilon convolution xi, where rho epsilon is a family of modifiers. So now psi epsilon is smooth. Oh, sorry, I see a typo in the equation now. I did not put, sorry, no, the epsilon is on 0. This is, of course, nonsense. The epsilon as an index should be on xi. So you have this regularized noise in the equation, and you study a new equation, which is, so whose solution is now classical. It's called psi hat epsilon. Okay, but the solution has to be modified or renormalized. So you have to add this linear term in psi hat epsilon multiplied by this constant, which is the sum of 3 terms. So one term in 1 over epsilon, one term in log epsilon, and one term which is, say, a constant. Maybe this could be R epsilon, which converges anyway to a finite value. So I don't know, maybe this does not shock the audience today, that you have to renormalize your equation in order to have a convergent family. So anyway, this is the case. If you don't put this red term, you will not have a convergent object. And it turns out that if you do this modification, you do have a convergent object, and the limit is what the physicists wanted to construct. So this is the correct solution, this psi hat here, which is the limit of psi hat epsilon. Again, psi hat is a distribution, and it is called the renormalized solution to the original equation. So I wrote that C1 and C2 are fixed, so they are given by the model essentially, just as the powers which appear, so 1 over epsilon and log epsilon. While R can vary. You can more or less choose it, and in general, the solution psi hat depends on R. Okay, you can see that the approach is, so the approach, at least the result is non-perturbative, so there is no small parameter lambda here, and this is one of the advantages of this approach. okay, once again, the equation, again with the same typo. So let me summarize or maybe stress an important point. So here we have a finite family of renormalization parameters. So in this case, this is R. So it is not C1 or C2, which are fixed, but it is R that you can choose. It can be 0, it can be 10, it can be minus square root of 2. So on one hand, you have a plurality of solutions because R acts on the possible solutions, but at the same time, you have a uniqueness statement once the renormalization parameters are fixed. So this is the uniqueness I was mentioning before. Okay, in particular, for every choice of the renormalization parameters, there is a unique solution, but for different choices of the renormalization parameters, the renormalized solutions can possibly differ. So this is maybe not always the case, but in general, they change. So in this sense, you have a uniqueness statement, but also you have renormalization ambiguities. There are some parameters which need to be fixed. Okay, this is, I think, the last slide on this part, and then I move to the algebraic QFT side of the story. So in this recent preprint, we use techniques which are borrowed from algebraic quantum field theory in order to compute essentially the correlation functions which are expected for the solution to this equation. Okay, so now we need the small parameter lambda. Therefore, the approach is perturbative. And also with this approach, one has to deal with the ill-defined, say, objects or distributions and ambiguities due to renormalization. But so interestingly, so these appear in a different way, in a different setting. And again, the aim of this project is to say, explain the two kind of renormalizations at the same time, the same context, although we are not quite there yet. So let me now explain what we do with this equation now. Okay, we consider the fundamental solution, the green function of delta, and we write the equation in this, it's called the mild formulation. And then we replace, if you want, a G convolution psi by some smooth function phi. Okay, I write here phi is in C infinity on the torus. And now capital psi is the solution to this equation, and it is seen as a function of phi, right? So now you see, if I replace G convolution psi by phi, I have completely eliminated the randomness. Phi is a generic, say, test function. And so this is maybe even more problematic. So I have replaced the distribution with the C infinity function. So now I am putting under the carpet the problem of polynomials or nonlinearities of distributions, but so this will come back a bit later. So of course you could ask me, how can this simpler, different problem help to describe the original one? So just wait for a second. So okay, I hope this is clear. So I have written now a deterministic, say, classical problem. And now I want to convince you that this can, with some work, help to describe the original equation. Now, since I have a parameter lambda, I can try to write the solution capital psi, which is a function of lambda as well, as a formal power series. So here I am fixing small phi. And now it is more lambda, which is varying. And then I write this formal power series. Where so now I am smiling because I remember so how many times I have discussed with Kurush and Federica on formal power series. So now I am back with a formal power series as well. So you have a functional a family of functionals fj, which are functionals of phi. Now they don't depend on lambda anymore. Okay, which are take values in C infinity functions. Okay, so and are polynomial functionals of phi. Okay, of the C infinity function phi. In fact, if you apply formally the equation to this power series, you obtain explicit expressions for all coefficients. So F0 is phi, F1 is this, F2 is this, and then you have a recurrence formula which gives you all terms of this formal series. Okay, so at this stage everything works nicely, apart from okay, recall these are the expressions from the previous slide. Now the problem is that first the series may not be convergent. Okay, this is well known in this perturbative approach, but this is not the only problem. So if I want to replace again phi with G convolution xi, which is a distribution, then okay, F0 is well defined, but all other terms contain powers of this distribution. So again, I am stuck. I don't know how to define properly these functionals. Okay. So let me explain another object now for a couple of slides, which is Wick polynomials. So if you have a Rk now valued random variable, which has all moments finite, so you take a power, so n here is a multi-index, you take so x1 to the n1 product, blah, 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 xk to the nk, absolute value expectation. This is supposed to be finite for all possible values of n. And then, so there is a construction of so-called Wick polynomials, which can be characterized as follows. So you have a unique linear map W from the polynomials of k commuting variables to the same polynomials, such that, so W is the identity on the constants, W commutes with the partial derivatives, and the expectation of every, say, W of x to the n is 0 for any non-zero n. Okay, so W of x to the n is the Wick polynomial of degree n. So you have existence and uniqueness of this family. Okay, let me immediately quote a wonderful paper I wrote with Kurush, Frederica, and Nicolas a few years ago, where we studied this construction with a Hopf algebraic approach, and we also studied this notion of deformed products. So once you have this map W, you can introduce immediately two different deformed products on the algebra of polynomials by, okay, how do you say, I don't know, kind of conjugation with this W so first you map Wxn, Wxm, you take the standard product, and then you go back by the inverse of W, or vice versa. And so the two products are different. So let me give you an example. So in the case where the averages are 0, and so Cij denotes the covariance between Xi and Xj, then the first product boils down between Xi and Xj boils down to adding the covariance, and the second product boils down to subtracting the covariance. Okay, so the second one is the one which centers these variables. Okay, so again, this can be seen in a Hopf algebraic setting with nice relations to the moment cumulant algebra. Okay, now, in fact, we would like to do something similar, but if we replace this finite dimensional vector with our random distribution. Okay, so now the parameter I becomes the space parameter X in the torus, and therefore, so we have an infinite dimensional vector, if you want, this distribution. But you can think, you can conceive an analogous construction. Okay, so for Gaussian, which is the case in our distribution, for Gaussian vectors, the mean and the covariance determine fully the law. So in this setting, our distribution is centered, but so the covariance function is given in this way. So it is the integral in dz of gxz times gzy. The problem is that this object is well defined only for x different from y in general, at least for larger dimension, because g is a singular integral kernel. Okay, so at least for d less or equal than 3, everything works nicely, and one can give a meaning to an algebra, say a deformed product of on the algebra of polynomial functions of phi. So for example, so this would be, sorry, the analog of what I wrote, sorry, this is going, okay, of what I wrote here, of this first product, okay? So now phi is a linear functional, so capital Phi, sorry, is the linear functional of phi, which associates to phi, well, phi itself in this case, but you also consider this as a distribution, and you compute it against this test function f. So this is to explain the notations. F is always a test function, and what we construct are distributions. Therefore, you must have linearity in f, while you expect a polynomial behavior in phi in general. So indeed, in this situation, you see, you deform the standard product, which will be just the square of phi, by adding the covariance, and in this case, you obtain this expression, which is well defined up to dimension equal to 3, because okay, the singularities of G are not too bad up to the dimension 3, while they become okay, worse from dimension 4 on. Okay, so now the question is, how can we make sense of this in higher dimension? Yeah, again, so this is the formula. So as I said, in high dimension, this expression is ill-defined, since Q is well defined only as a distribution of the say product, so the torus times itself minus the diagonal of this product. Okay, so however, this is what I learned from my colleagues, my co-authors. So there exist techniques which are called microlocal analysis, which allow to extend this distribution Q on the diagonal to a distribution on the full product. And okay, so there are two separate steps, and the next step is to give a meaning to the restriction of this extended distribution to the diagonal. Okay, so you need to do both things. So this approach is based on the study of the wavefront set and of the scaling degree of these distributions, which we are studying, and doing all this, so which is a long series of non-trivial considerations, you obtain a well-defined product where now what appears in this integral on the right-hand side is in fact a true distribution on the torus. Okay, so you can define a deformed product on these objects, capital Phi's, and so an algebra defined by these objects, which are, again, so as is seen from the right-hand side, so you see these are polynomial functionals of Phi with values in distributions on this state space, the torus. Okay, so this head P is a distribution. So you have to accept that even if Phi is smooth, what you obtain in the end is only a generalized function, a distribution. Okay, again, so we have obtained existence of this well-defined renormalized product with this pi hat, p hat, which replaces the covariance of our random distribution. And again, more generally, we can define an algebra of such distribution-valued polynomial functionals. And this dot Q is the product on this algebra. Now, what about uniqueness? In fact, if D is greater or equal than 4, there is no uniqueness of such a product. There is a family of possible choices for dot Q, and actually also for the algebra itself. And these are the ambiguities due to renormalization. So these are the parameters that one has to fix in the theory, and they can be fully characterized. So, for example, if you at this level want to change the product which is there, so you can change p hat, and in fact any other choice will be the first one, say, plus a constant. Okay, so this characterizes the space of possible choices at this level, and then so there are constraints at all levels. Now, why did I introduce all that? So let me go back to the equation in the perturbative setting. So you remember I had this nonlinear, say, PDE with this small phi as a kind of say variable, so that psi is a function of phi. I write this as formal series, and I have all these explicit expressions for my objects. Okay, but sorry, so this is no, okay, what I wrote here was not maybe really what I had in mind. So now this is not really defined, but this is not good to to describe the behavior of phi. So of all this, when phi looks like a G convolution psi, okay, this is maybe the correct sentence to put here. In fact, what is a better description of my original problem is the following. So I replace the standard product I was using until now with the one possible choice of deformed product. Renormalize the product. So this is, in fact, you see, very similar to what was done in the singular SPD setting. So I had a ill-defined nonlinearity, and I had to modify this nonlinearity by modifying the product, and then I had renormalized the equation and I renormalized the solution. Here I'm doing the same. But at this level, which is not really random, it is deterministic, but the new product which is introduced describes or mimics the behavior of these random distributions when this G convolution psi is the driving object. Okay, so this is, anyway, as far as I understand, the point of view of algebraic quantum field theory, and again, so I have an equation which can be written also more explicitly in terms of the original product. I can write now psi hat as a formal power series, and I have explicit expressions for all levels. Now, as I said before, there is a difficulty, which is the following, that all these f hat j now makes sense as distribution valued polynomial functions of phi. Okay, so f(0, 1), so sorry, f(1 hat), for example, is a distribution, and all following terms as well. Now, what was the original aim? So if I now go back to the stochastic PDE, but with the parameter lambda included, okay, so I would like to try to describe some, for instance, the correlation function. So this is mentioned below in this slide. So, for example, I did not write the correlation functions, but one possible formula that we expect to have is that if we consider the solution to this PDE, which is a distribution, so the renormalized solution to this PDE, so the true object, which is well defined, it is a distribution, it depends on lambda. I test it against a test function f, I take the expectation, and so this may be, okay, the series of the lambda to the j, f hat j, etc., with phi equal to 0, okay? So maybe the series is not convergent, but then this can be recovered in the sense of the derivatives of lambda computed at 0, etc., okay? So we expect that these functionals that we have computed give some non-trivial and interesting information on the singular SPDE, on the renormalized solution to the singular SPDE, which would be maybe, so this is expected, but still my colleagues in singular SPDEs have not too much looked into this direction. Until now, the main aim is to construct solutions, to construct these renormalized solutions, but not so much to then compute some functionals. Okay, so this looks to me an interesting problem, and we conjecture that with this approach it is possible to obtain some of these non-trivial say information. And by the way, yes, another question which is natural is to recognize so the different sets of renormalization constants and match them. So this is also a reasonable question which should be addressed in our subsequent work. Okay, so this was my last slide, and I'm happy to finish 6 minutes in advance. Thank you very much for your attention.
Thank you very much, Lorenzo. Thank you. Thank you for this bridge-making talk. You're bridging huge gaps, and that's a real challenge. Thank you very much for this very comprehensive survey of what you're working on. I see that there were questions in the chat and in Zulip. Anyone want to raise well, formulate a question?
Yes, can I ask a question?
Yes.
So Lorenzo, is there a way to connect your normalization approach to the other ones? So can we understand if they can be connected directly or something like this?
What do you mean by your?
So this construction you presented.
Yes.
Can you connect it to the other ways of normalizing stochastic differential equations, or is it a totally different approach?
No. Well, this is what I say in the last sentence of this slide. No, so I'm saying that we think that we should be able to translate one into the other. So we have not done this yet, but so the constants should be the same, and we should be able to see where they come from in both settings. Is this what you mean?
Well, the question was more philosophical in a certain way. Is there a reason why you expect the two normalization processes to agree, or is it just a conjecture or something you hope?
Well, again, maybe my co-authors want to intervene. I am modest. I don't ask myself too many philosophical questions. So, Claudio or...
Hi, Lorenzo.
Hi, Claudio. Please.
So, of course, it is still at the level of conjecture, but we expect that all renormalization schemes should be comparable between each other. At least the experience coming from, let's say, hyperbolic PDEs and theories on, Lorentzian manifolds suggests that all renormalization schemes are connected. Of course, it has to be proven, so it is still at the level of conjecture.
May I ask at this point, what about the renormalization group? Of course, it's in the background. Can you describe them?
Well, again, maybe we don't have yet a general picture in mind, but in this concrete example, I think that it is simple to see that indeed, so the constants are the same. So the groups which act on the families of solutions are isomorphic or just the same.
Can you? What my question was? Can you give an explicit isomorphism?
Yes, I think so. Yes. So again, this is part of our project. there may be results on specific models, and then maybe more general results. So I don't want to make too bold statements at this stage, but we certainly hope that this is possible.
Thank you. More questions?
Question for Lorenzo.
Can I have a quick question, please?
Go on, please.
So I was just wondering, so there's this connection, obviously, with perturbative approach. Can you use this approach to construct non-perturbative models in algebraic quantum field theory? Can you use that bridge to get some non-perturbative things going?
Yeah, so this was one of the first attempts to go in that direction. Then, okay, we got stuck in some technical difficulties, and we found that this, which was more, say, treatable problem. But again, yes, we are discussing how to translate Martin's theory, for example. Actually, even Massimiliano's theory would be a good tool in algebraic quantum field theory models.
That would be super interesting. Wow. Okay. Yeah, it's very good. So the technical problems are new technical problems or old technical problems?
Well, they were new to me. I don't know about Claudia.
No, they are relatively new technical problems. They are completely different from the Lorentzian side.
Okay. Good. Yeah, I would like to learn more about it. Thanks, Lorenzo.
Thank you.
I think there was another question I missed.
I also want to ask a question.
So I have a question for Lorenzo. Okay, thank you for the nice talk. At the beginning, you mentioned a formal series, and now you have you should have a real series, so a true series. So now, what are the conditions? I mean, and you mentioned also a perturbative expansion. So at the end of the day, in which range your lambda stays, and where do you have a real true series, and where you have a formal series? So,
okay. Yes, but this again, also this slide is also this formula is a conjecture. I'm not claiming that the series converges. Maybe it does not. Then you just take derivatives
okay.
So left hand side in lambda, and you compute at 0. That would be already interesting.
No, but it was just to say, because you started with this formal series, and after you put some product, and maybe you calculated the way when lambda is, so you mean
in the previous slides?
Yeah, exactly.
Like here.
Exactly. So if you take this, I mean, this psi hat lambda maybe is a real series when lambda is some range and so on. So, but you still in the formal setting. So that
maybe no. This is still formal. Yes.
Okay, this is still formal. Okay, thank you.
Because anyway, the expressions for the f hat are very simple. So at this stage, you don't really need the series to converge.
Yeah. Okay, but.
David, I see your hand. You raised your hand. Is it you want to ask a question? Maybe not.
I would like to ask a question, if it's possible.
Yes.
Yeah.
Yes.
Hey, Lorenzo. I have a more general question, maybe very naive. Or you do this type of expansion if you have a true nonlinearity, not a polynomial one?
Well, how do you do that in higher dimensions? So.
But do you know, for related structures or paraproducts, it was the big difficulty was to linearize a smooth function applied to U polynomials. I mean, you do either locally or with linearizations here, or you do that, or maybe it's not. You are not at this point.
No, we are not at this point yet. It's an interesting problem, but no, we are still on simpler questions.
And just a remark, when you put this lambda in the system, I mean, it reminds me when you look at the error custom model, when they put epsilon in front of the dxu square in order to increase the power of dxu. And this way they got expansion when there's this parameter everywhere. And this epsilon helps them for proving the convergence of this.
Yeah, I also had the same thought. Maybe it's a way to go in that direction. Yes, I agree. Thanks.